Okay, in the last video, guys, we talked about how logarithms were inverse operations of exponential models. We said that it's like undoing the exponential. So another way of saying that is we use logarithms to find the x value in the exponential models or functions. So we use them to solve exponential models and functions. Okay, and remember that in an exponential function, those are the equations that have the variable in the power. And we also said that a logarithm by definition looks like this. If I have log of any base b, of y equal to x, that's going to be the same as saying that base b to the x power is equal to y. And we remember we said this was the exponential version, exponential form, and this was the logarithmic form. So the logarithmic form depends on the exponential form. That's how we define it. Okay, and then so the common logarithm is simply going to be a log that has that base 10. And in the calculator, we said it's often written as just log without the base 10 written. Okay, so just remember that if someone ever says use the common logarithm, they're saying log base 10. The natural logarithm, that is going to be log base e, and that's always written, like the button on your calculator is written as ln. Okay, that's an L. Sometimes I'll write it like a cursive N, ln. In case you see that, that's what that means. All right, so that means if anyone says use the natural base, we're talking about the base equaling e. So we usually don't see it written like this with the e written, but I want you to see how it corresponds to the generic logarithm definition. So now let's look at the graphs. And I want to take you back to the exponential graphs so you can see how the logarithm and graphs compare. All right, so in the exponential graph video, we plugged in a bunch of numbers for x, and then we actually just did 2 to the negative 2 power, that was 1/4. 2 to the negative 1 was 1/2, 2 to the 0 is 1, 2 to the first power is 2, and 2 to the second power is 4. And then we graphed them, and we found a function that looked like this. And we said, oh, there's an asymptote, a horizontal asymptote on the x-axis, so it never goes beyond that. And then it goes up really quickly. That was our exponential function. So the logarithmic function is going to be the inverse of that. So going back to our inverse functions earlier this semester, we said that the inverse function switches the x and y coordinates. So I'm going to take that blue x, y table and I'm going to switch them around. So for x, I'm going to have 1/4 and the y value is -2. Then the next one would be 1/2 comma -1. And then 1 comma 0, 2 comma 1, and then 4 comma 2. So let's see what that looks like when we graph that. So if I go to x is 1/4, and then that's like -2, that's like there. And then 1/2 -1 is here. 1 0 is here. And then I have 2 0, 2 1, and then 4 2. So if I were to keep going, it would look like this. So this one has a vertical asymptote. It's going to get very, very close to that vertical line, and then it's going to spread out as you go further along in your table. Do you notice how in this one there are no negative numbers and there's no 0? That's because over here we never had answers. We're always above 0, right? They never equaled 0, and they never went below that into the negative parts. So that's why that is the way it is. So that's going to affect things like domain and range. So let's recap what we knew about exponential and then what we're seeing about logarithms. So in the exponential, we had our y-intercept was at 1, and we had a horizontal asymptote at 0. We said our domain was always all real numbers, and that our range here, it was always y is greater than our horizontal asymptote, or we said k value, right? Here there's no k value. Remember, it'd be like I would be adding 0. Over here, what do you notice? We don't have a y-intercept, we have an x-intercept. Our x-intercept is right there, and that's at 1. Okay, we have a vertical asymptote at 0. Here, our domain, our x values, we said that they're never going to be negative or 0. So our x values are greater than 0. And if you notice here, we're going to talk about this later, that's bigger than our h value. And I'll talk about that later. And then our range is going to be all real numbers. All right, so everything is flip-flopped with exponential functions and logarithmic functions. So if you remember exponential, all you have to do is flip-flop it for the logarithm, and that'll help you with logarithmic graphs. Okay, so let's write some general forms of our logarithmic functions. That was one specific example. So we're going to have y equals, you can have some number in front of your log, that's okay. The log can be any base. And then you're going to have x minus h plus k. Hopefully that looks familiar. Okay, and this is where the asymptote is the h value. X equals the h value. The graph of a logarithmic equation has a vertical asymptote, like what we just said. We also said that the domain is always going to be x is greater than our h value. Okay, so that depends on where that vertical asymptote is. If it's at 0, then x is going to be greater than 0, like in our example. If it's something else, then we have to change the domain to be x is greater than whatever that h number is. The range will always be all real numbers for a logarithmic. Okay, so recap on the h. So if there is an h value, the graph moves left or right in the opposite direction. Okay, so that says direction. So, for example, if I had log base 3 of x minus 7, I would know that this is going to move to the right 7 because that h value is positive 7. It's opposite of how I see it in the equation. Okay, if there is an k value, the graph moves up or down in the k direction. Okay, so for example, if I had log base 3 of x minus 7, notice that this is different than the green one that I wrote. I don't have parentheses around it. That's how I know that the red net minus 7 is a k and the green minus 7 is an h. So because that 7 is negative, that k value is negative, it's going to be shifted down 7. Okay, so let's look at some examples of graphs. All right, we're going to graph this one. I'm going to pick out those pieces that we were just talking about in the general form. Notice that my base is 1/2, and then I'm going to have my h value. Notice that there's no parentheses here, so my h value is 0, and my k value is -1. So that tells me quite a bit, doesn't it? As far as shifts go, it's not going to shift left or right, but it is going to shift down 1. Okay. And as far as our domain, we just said that our domain has to be x is greater than our h value, which is 0. Our range is always going to be all real numbers. And our asymptote is x equals whatever our h value is. So here it's going to be 0. So I know I'm going to have that asymptote right there at x equals 0. So when I'm making my table, I shouldn't try to plug in a negative number or 0 in for x. Okay? We're going to be plugging this into this function. okay? And remember, if you're doing this mentally, you could do this in the calculator or you could do this mentally. I like to think of it mentally because it's easier for me. I don't have to grab a calculator. So remember, when I'm doing just this part, not the -1 part, but just this part, I'm saying to myself, 1/2 to what number, that's the y, right? So the y value equals my x. So some really easy ones to start with are some fractions. So let's say 1/2 to what number equals 1/4. So I'm going to make 1/4 my first x value. So what would that have to do? I would have to square that. So my y would be 2. Then I'm going to do another fraction. Let's do 1/2. So I'm picking my x values carefully so that I get nice numbers for my exponents. Because I know that 1/2 to the first power is going to be equal to 1/2. So I know that my y value would be 1. Oh, I'm forgetting. That's just the blue part, right? I totally forgot to do the -1 part. That's right here. So actually, I have to do one more step on all of these. I need to subtract 1. So this is actually going to be equal to 1 here. This is going to be equal to 0. That's that shift down. That's why all of those are shifting down. And then let's see, if I do, what's another good one to do? How about 1/2 to what power equals 1? Well, we know anything to the 0 power is equal to 1. So I know that my power, my y, would be 0. And then I would have to subtract that 1. So that gives me -1. So I'm using those black numbers. That's what I'm going to actually graph. Let's do 2 and 4. Notice I'm skipping 3. And again, the reason is that I know that I can't do a whole number as a power and get 3. So if I wanted to get 1/2 to some power equals 2, then this is going to have to be a negative answer because it's going to flip-flop it. So that's going to be -1. And then I have to subtract 1 from that. So that's going to end up being -2. And then my last one, 1/2 to what power equals 4? Well, that's going to have to flip-flop, so that's going to be a negative, and then 2 to the second power is going to give me 4. So that's -2, then I'm subtracting 1, and that's going to give me a -3. So let's graph all of that and see how that turns out. All right, so I'm going to graph 1/4, 1, 1/2, 0. So notice that my x-intercept is different because I have a different base. At 1, I'm at -1. At 2, I'm at -2. And then at 4, I'm at 1, 2, 3, 4. Here's 4, I'm at -3. So here's what this one looks like. So do you see how this one, it's getting further away from the x-axis, but it's going down instead of going up. And it hugs that asymptote. It's getting closer and closer to that vertical asymptote there. Okay, so that one looks different because our base was a fraction, 1/2, rather than a whole number like the 2 that we just did. All right, let's do one more. Log base 5 of x plus 2. So again, my base is 5, and here this time my h is -2, and my k value is 0. It's like I added nothing. The k value is 0. So this means that it's going to shift to the left 2. Okay, I know it's to the left. It's opposite of that +2. So -2 means left 2. And it's not gonna go up and down, right? It's not gonna shift up and down because k is 0. All right, so our domain is gonna be x is greater than -2. My range is always all real numbers for logs. And then my asymptote is x equals -2. If we do that first, it really helps with the graph because I know that I'm gonna have an asymptote right here. So you see how it's no longer on that y-axis anymore. It's not at 0, it's shifted to the left too. Okay, so now when I make my xy table, okay, I can pick anything that's greater than -2. So I could do like negative What could I do that would be nice and easy? Like -1. I could do 0. I could do 1 and 2. All right. These numbers aren't going to give me really nice numbers. Remember how last time I was doing really nice numbers? But that's okay. We can still plug them in. All right, so we are plugging in log base 5 of, I'm going to plug in -1 plus 2. So what I'm actually doing is log base 5 of 1. So 5 to what power equals 1? Well, we know that one. 5 to the 0 power gives me 1. Okay, and then the next one we're doing is log base 5 of 0 plus 2. So this is one that's going to turn out kind of funky. So log base 5 of 2. So if I say 5 to what power equals 2, then yeah, that's where we're going to have trouble, isn't it? So here's where I'm going to show you in the next video how to do this on your calculator, and I'll show you in class as well. But we're going to do log base 5 of 2 in our calculator, and that gives me 0.43. All right, so next thing I'm doing, log base 5 of 1 plus 2. That's going to give me 5 to what power equals 3. So again, I'm having trouble with that. I have to use my calculator because I can't just look at that and know. That gives me 0.68. So what if we skip 2? Because I know that if I do 5 to what power equals 4, that's not going to give me a good number. How about if I do 3 instead of 2? That would mean that I'm going to do log base 5 of 3 plus 2. So that's doing log base 5 of 5. And that means 5 to what power equals 5? Well, I know that one. That one's 1. Okay, so if I start graphing these, at -1, I'm at 0. At 0, I'm at 0.43, so it's like barely above. And then 0.68, kind of in the middle. And then at 3, so that's 1, 2, 3, I'm at 1. So it's looking like this. Okay. So when we pick them, if you want to pick easy numbers, you want to think about things that are easy to do with that base that you have there. If not, if that's confusing to you, then just use your calculator, and that's what we'll do in the next video.